we're going to take a look at some vectors in this section, and we will focus exclusively on vectors in the first quadrant for now. In the next semester, in Pre-Calc 2, we're going to extend this to the entire plane. A vector is a quantity that has both magnitude and direction, and we're looking at vectors in 2 dimensions. So drawn on the plane, you could think of it as a directed distance, right? So it has magnitude, which is the length, and direction, which is the angle. So the magnitude is this bit right here, and the angle here, that's the direction. We refer to the whole vector, usually we use letters like V and W for vectors, but we'll indicate that it's a vector by putting a little kind of half arrow over it, like I've done here. In textbooks, they'll usually indicate it's a vector by putting it in bold, like that. Only if we're just writing things out, that's harder to do. So it's common to use that little arrow on top of the letter to indicate that it's a vector. The magnitude is really defined is how we define the absolute value of a vector. It is its magnitude, and of course the direction is the angle. So we have a vector v, and it is defined by a magnitude at a given angle. One of the things we're going to do in this section is learn how to add vectors. Now visually, if we add them kind of graphically, we add them tip to tail. So what that means is, if we look over here on the right, I've got 2 vectors drawn in blue. I've got vector v and vector w. Now if I take vector w and I slide it so that it starts at v, that's what I've drawn here, sort of in the mint green here. I redraw w just with a different starting point, so I'm not changing the angle or the length. I'm just sliding it up, and then I see where it ends. Then if I draw the vector from the origin to that endpoint, that is the sum. Now here I've drawn w so that it starts at the end of v, but I could just as well draw v so that it starts at the end of w. And if you do it in either, if you do it in both ways, you end in the same spot, which is good because it doesn't matter what order you add vectors in, you'll end in the same spot. But you can also see it kind of forms a bit of a parallelogram there. We can also multiply a vector by a scalar. A scalar is just a plain old number, right? So a vector has magnitude and direction. A number really just has magnitude. It's just a plain old number. And that just changes its magnitude. So if I have this vector v drawn over here on the left, now look over here on the right, 2v is just the same. I'm not changing the direction, I've just made it twice as long. I've just changed its magnitude. If I multiply a vector by a negative, it just flips it around, so it's like a 180 rotation. So there's negative v drawn right there. What we're going to do, in order to have a more rigorous and easier to compute way to add vectors, we're going to define components of vectors. So look, we define a vector, right, as something that has magnitude and direction. So let's say I've got this vector v. It has some magnitude, right, and it has this direction. The components are really defined to be, if you take that point where the vector ends, the components are the coordinates of that point. The x component is the x coordinate. The y component is the y coordinate. Now up here at Theorem 2, we have these formulas, right, that tell us how to find the x component vx and the y component vy. Magnitude times cosine theta, magnitude times sine. Now you're going to use those a whole bunch, so maybe it'll be fairly simple to commit to memory, like just by doing enough practice you'll kind of remember. But if you forget, it's actually pretty simple to see why those formulas are the way they are. So I've drawn this vector, and we're going to do one of our favorite things in the plane, and that is to drop down a perpendicular. So there's a right triangle. So now I know that this length here has to be the same as the x component. this length here has to be the same as the y component. Now let's think SOHCAHTOA. We take the SO part of SOHCAHTOA, then sine theta is equal to Vy over the magnitude. And if I multiply both sides by magnitude, we get that Vy is equal to magnitude times sine theta. Similarly, if we take the cosine part, the cosine part of SOHCAHTOA, we find, let's see, we get cosine theta is equal to adjacent over hypotenuse is now Vx over magnitude. If we want to solve for Vx, we're going to multiply both sides by the magnitude. And there we get Vx is equal to magnitude times cosine theta. So this is, right, this is exactly what we have given up here in Theorem 2. If you know, I guess one of the big things to take away here is just to note that working with vectors is really an application of our right triangle trig. So kind of if you can remember Pythagoras, if you can remember SOHCAHTOA, even if you have a harder time remembering these formulas here, you'll be able to derive them for yourself. And just to be complete here, we were talking about SOHCAHTOA, the TOA part. Tells us that tan theta is equal to Vy over Vx, and that'll be important in a little bit. So when we find the components, sometimes the problem will say find the components. Sometimes it will say resolve this vector into its components, which just means find the components. So here they've given us magnitude and direction. We want the components. So that's 14.4 times cosine of 82 degrees for the x component. If I want the y component, that's magnitude times sine theta. So 14.4 times sine of 82 degrees. Now, before I calculate these, I'm going to just sketch what this vector looks like. It's not going to be exact. It's not going to be anywhere near exact, but I'm going to get a little rough idea of where this vector is. We know that we have all, first quadrant vectors in this section. 82 degrees is pretty close to 90 degrees, right? In fact, it's probably even closer than that, but that's what I got. So here's 82 degrees. And this is length 14.4. And what I'm looking for, right, are these coordinates. So look, if I were to think about this, dropping down this perpendicular, there's my Vx, there's my Vy, and I'm doing this simply to give myself some perspective. Vy is going to be a lot more than Vx, should be a lot bigger, right? Vx will probably be pretty small, and Vy will be large in comparison. So this vector is mostly y component with a little bit of x component. Now let's calculate this. I get 2.004, I'll just say 2.00. They use 3 significant digits there, so Vy (14.26) or 14.3, 3 significant digits. So yeah, mostly y component. Vy ended up being a lot bigger than Vx. Alright, let's do another one. Here they ask us to resolve this vector into its components. So we have a magnitude of 20.8 an angle of 13.2 degrees. So this one's already been drawn for us. 13.2 degrees, pretty shallow angle. So I'm going to expect this to be mostly x component. I'm going to expect the x component to be bigger than the y component. Vx is magnitude times cosine and Vy magnitude times sine (20.3) approximately for Vx, and Vy (4.75). And our kind of observation was borne out here. We see that the x component is quite a bit bigger than the y component. So if we're given magnitude and direction, we can find the components. Now if we want to go the other way around, if I know the components, all right, so I'm going to scroll back up here for a moment. If what I know are the components, I'm given Vx and Vy, then we can find the magnitude by using Pythagoras, right? Because I know that the sum of the squares of the two legs, right, Vx squared plus Vy squared should be the square of the magnitude. And we can find theta by using this fact right here, right? I know that tan theta is Vy over Vx. So the arctan, we can use the arctan function. And that's what we have here in Theorem 3. So in example 119, we're going to find the magnitude and direction for a vector that has components Vx equal to 5.2, Vy is equal to 9.7. So let's see, if we're going to find magnitude using Pythagoras, since we're solving for the magnitude, I'm just going to jump straight to this radical formula, right? Pythagoras directly says the square of the magnitude is the sum of the squares of the two components, but we know we'll just take the square root to solve. So we have the square root of Vx squared plus Vy squared 5.2 squared plus 9.7 squared I get 11.005. I guess I'll just call that 11 because it's the same number of significant digits as the components. Now for the angle, let me just sort of look at this. I know the components. 5.2 is x, 9.7 is y. Okay, so let's pretend that's drawn a little bit nicer, but 5.2, 9.7. Now the y is a lot bigger. I'm going to expect that this angle will be bigger than 45 degrees. At 45 degrees, the x and the y components would be equal. But the y component is bigger, which I think is going to force the measure of the angle to be higher than 45 degrees. So I know that tan theta is equal to Vy over Vx. So theta is arctan. Vy over Vx, that's 9.7 over 5.2. I get 61.8 degrees. So we have found the magnitude and we have found the angle, and we could we could leave it there. Usually if I'm finding a magnitude and direction, I go ahead and I just state what the vector is in that form. So my vector v is equal to a magnitude of 11 at 61.8 degrees. Okay, now that we know about components, we know how to find components, we know how to find magnitude and direction if we have components, now we can really talk about how we add vectors, right? How we actually physically add them. So we know that graphically we can add them tip to tail, but that usually, if we rely solely on that, then we just kind of have an eyeball, like, approximation. We can kind of eyeball where it's going to end up. It's not very precise. So to get a more precise answer, what we're going to do is follow this procedure. And let's say I want to add two vectors, say V and W are two first quadrant vectors. Then we can find, we can add them together. We can find their sum, which we call the resultant vector, and that's why I'm calling it R here, by doing the following. So first we're going to find the x and y components for both of the given vectors, for V and W. Then I get the x component for the resultant vector by just adding the two x components together. I get the y component simply by adding the two y components together. So once I know Rx and Ry, then we're back to what we just did on the previous example. If I know the components, I can get magnitude and direction by using Pythagoras and arctan. So we're going to do this a couple of times. We're going to add these two vectors. V is the vector 1200 at 10 degrees. W is the vector 1750 at 35 degrees. So let's focus first on the vector V. So we know that Vx is magnitude 1200 times cosine of the angle 10 degrees, and Vy is magnitude 1200 times sine of the angle 10 degrees. Uh, 1181.77 for the x component, and for the y component, 208.38. Okay, so there's the V vector. Now W, 1750 at 35 degrees. So Wx, 1750 times cosine of 35 degrees, and Wy is 1750 times sine of 35 degrees. So 1433.52 for the x component. And the y component, Wy, is 1003.76. Okay. Alright, so now Rx is Vx plus Wx. I'm going to add these two together to get Rx 1181.77 plus 1433.52, 2615.29. And our y is Vy plus Wy. So I'm going to add these two things to get that. 208.38 plus 1003.76. So it's 1212.14. Okay, now we have our two components, but we're not done, right? So sometimes people will stop once they found our x and our y, but if you want to add vectors, you want an answer that is a vector, and you always want to give it, unless specified otherwise, you want to give it by using the magnitude and direction. So two more things left to do. Magnitude of the resultant vector, square root of the sum of the squares of the components. We get 2882.54. And theta is arctan of the y component over the x component. So 1212.14 over 2615.29 inside an arctan function. We get 24.9 degrees. And so now we're just sort of putting this together. Our resultant vector is 2882.54 at an angle of 24.9 degrees. And that's basically how we add two vectors. It's a bit of an involved process, like there's a lot of calculations that we have to do, but it is also very algorithmic. It's a very step-by-step process. Find components, add x components to get x component, add y components to get y component, and once we have our x and our y, we use Pythagoras and arctan to get our magnitude and direction. We're going to end with an applied example here. Lots of quantities, in the world are physics, are vectors. So we see a lot of vector applications in physics, and in fact, being able to do a little bit with vectors. The reason we do this first quadrant trigonometry first in the beginning of this class is so that we can understand a little bit of vectors for when you encounter them in physics. So forces are vectors. Velocity is a vector quantity. Displacement is a vector quantity. And that's what we're going to see here. A ship sails 15.2 miles due east, then turns 31.25 degrees north of east. After sailing another 26.18 miles, where is it in reference to the starting point? So, the first thing I'm going to do is sketch this out. So here's my first quadrant plane coordinate vectors. It says first it goes 15.2 miles due east. So if this is the starting point at the origin, 15.2 miles due east. Then it turns 31.25 degrees north of east. So that's maybe about that angle right there and goes another 26.18 miles. And we want to know where is it in reference to the starting point. So what we want is this vector. So I'm going to call this R. Like that's where it ended up. That's sort of the resultant. And you can see just the way we drew these, I drew one vector so that it started at the tip of the other vector. That's a tip to tail addition. Really, I'm adding two vectors. And so this first vector, 15.2 miles due east, I'll call that D1 for the first displacement. And then this vector is D2, but I'm going to draw it so that it starts at the origin. So this is D2. It's 26.18 miles. And the angle here is 31. That angle there is 31.25 degrees. So I need the components for D1 and D2. I could add the x components to get Rx and the y components to get Ry. So the D1 vector, that one's going to be easy to find the components because the coordinates of the point where it ends are pretty clear, right? The coordinates of that point have to be 15.2 and 0, right? Because the angle is 0. So we know that D1x is 15.2 and that D1y is 0. For the other vector, for D2, we'll need to use our formulas. So D2x is 26.18 times cosine of 31.25 degrees. And D2y is 26.18 times sine of 31.25 degrees. So D2x is 22.38. And D2y is 13.58. Okay, so now we have all of our components. Rx is D1x plus D2x. So I'm going to add these two together. 15.2 plus 22.38 is 37.58. And Ry is D1y plus D2y. So I'm going to add these two things together. Of course, D1y is 0, so Ry is 13.58. Now that I have the components, I'm going to finish this up by finding magnitude and direction. So the magnitude of the resultant vector is the square root of the sum of the squares of its components. I get 39.96. And this is where the units are attached, so 39.96 miles. And then the angle, it's important not to forget the angle. Sometimes when people find the magnitude of an applied vector problem, they think they're done, but we always want to make sure we get the angle as well. So theta is arctan of ry over rx 13.58 over 37.58. Get 19.87 degrees. So the resultant vector is 39.96 miles at 19.87 degrees. Now this is a standard position angle, so it's understood that that means 19.87 degrees north of east, right? So we're starting at the positive x-axis and going counterclockwise.